Okay, your exam grades will most probably be announced sometime this week. There is not much left to be graded. Well, if you don't want to, we can postpone it. Currently, it is 41. Well, you see, this is the curve of everyone, not just this classroom. Okay, you will learn your grades, don't worry. Any other questions about the subjects we are discussing? I don't know. You will learn the chapters to be included in the next exam, probably next week. Of course, I know the answer, but other questions about physics? Yes, questions? So up to now, we have been discussing about electric fields, and last week we were discussing the electric circuits, how to study the circuits, obtain the currents, etc. Any questions on those? Because from this week, we will start a new subject, which at least for some time, it will be radically different from what we had done until now. So we will start with the magnetic fields. Well, do you know where the name magnet comes from? Yes, magnesia. Did you check where it is? Where? It is Manisa. Yep. Read your book, preferably before coming to the lecture. Not while preparing for the exam. Well, that is the name comes from, where people had discovered that certain kinds of rocks attracted iron, and they attracted each other. And nowadays we call them magnets. And magnets have been used for quite a long time. So the nice property is they exert some forces on each other. You see, last semester in mechanics, you had studied and dynamics, you studied how various objects behave under an external force. This semester until today, we had been discussing about one kind of force called the electric force. And now there is this second kind of force that people call a magnetic force. So you have these rocks, and they attract each other. If you just hang one from the top, just balance them. I forgot to bring a magnet. We could have tested it maybe on Thursday. If you just hang a magnet, it always rotates, and eventually it gets the same orientation. So it always points in the same direction. So this was a great discovery, especially for navigation. So if you are, let's say, on the sea, on land, navigation is not that big of a problem. You have the trees, you have the mountains. You can just look at the mountains and decide which way you are moving. But if you are in the open sea, there is practically nothing to look at. And this just gave us a way. So, and I mean, until the discovery of the magnets, in fact, human people, they could only sail as long as they could see the land. So they could see the land, they could determine where they are. But with the discovery of the magnets, Now, they know their direction, and since they know their direction, they could just go wherever they wanted. Now, some observations about these magnets, they always had two different orientations. Let's say if you just hang a magnet like this, it always points in the same direction, and one of the directions is named the north, the other one is south, because one of them always pointed, and if you just arrange the shape properly, one of them always pointed towards the north, almost towards the north, and the other one always pointed towards the south. So that's why we call that the north and the south pole of the magnets. And if you have two magnets, the north and the south pole, and if you just put them like this, they just repel each other. This is the direction of the force. And if you just put them in the other way around, in the other way, meaning the north faces the south, they attract each other. These are just the basic observations. So the north pole of this magnet always points towards the north. So where is the north pole of the Earth if you think of it as a kind of a magnet? It's on the south. The magnetic north pole of Earth is on the south. Magnetic south pole of Earth is on the north. Because basically the magnetic south is attracting the north pole of the other magnets that you might have. So that's why the north pole is pointing towards the magnetic south. Well, the magnetic poles of Earth, they are not really fixed. They don't coincide with the geographical poles. You see, if you look at the poles, if this is Earth, let's say it is rotating around this axis, the north of Earth is this one. This is the north, this is the south. These are the geographical north and south. And the magnetic north is shifted, something like around 900 kilometers. So if you are using a compass, well, it doesn't always point towards the geometric north. So you have to take care of that deviation. And if you happen to come across a map, a navigational map, on the map, it always shows the deviation between a compass and the geographical north. So you know, if your compass shows that the north is in that direction, you know how much you should correct it to determine the geographical north. Now, well, when it was first discovered, we had no idea that this was related with electricity. This was just another kind of force. And in fact, later on, we had seen that if you have a compass, let's say this is the north, this is the south. And if you put a wire near it and send some current through the wire, the current causes the compass to deviate. So at least this showed us that there was some kind of a relation between the currents, the electricity, and magnetic force. On one hand, we know that the compass feels the magnetic force, but it also feels the force created by this current. So somehow we should be creating the magnetic field. Now, we will discuss all these in more detail. Let's first try to visualize these. You see, when we were discussing the electric field, we were saying that the electric field, we draw the electric field lines. Well, similarly, we can consider the magnetic field lines. So if you have a magnet with a north pole and a south pole, the magnetic field lines come out of the north pole and they go in the south pole. And what happens in between? Well, essentially these field lines, you can imagine them to continue. So basically, in terms of these magnetic field lines, north pole is the pole from which these field lines emerge, and the south pole is the pole through which these field lines submerge into our magnet. So let's just imagine we break a magnet. So you just break you have a magnet with a north pole here and the south pole there. You break it apart. Well, this is how the magnetic field lines will look like. Remember, they continue in the magnet. Well, now you see here from the surface, they emerge, they appear. So this is nothing but our new north pole. And here, they enter into the magnet. That's nothing but a south pole. So if you take a single magnet with a single north pole and a south pole, you cut it in half. At the end, you will end up having two magnets, each with a north pole and a south pole. Well, this is completely different from electricity. You see, if you have negative charges, electric field lines only enter there. They cannot leave. If you have positive charges, the electric field line just start from the positive charges. Well, we discussed about the dipoles, the electric dipole. In the case of electric dipoles, electric field lines started from the positive charge, and they ended up at the negative charge. But we could break it apart to have a positive charge and a separate positive charge and a separate negative charge. Here it doesn't happen. We did look for what is called a magnetic monopole. You see, this is a dipole. Just like if you imagine the electric dipole, it has a positive charge and a negative charge. One point where the electric field lines start, another point where the electric field lines enter. Here you see there is one part where the magnetic field lines start, and another part where the magnetic field lines enter. So this is a dipole. This is called a magnetic dipole. And magnetic monopoles do not exist. At least we haven't been able to measure them, observe them yet. There are theories that predict the existence of magnetic monopoles, but at least up to now, all the efforts to create them or to observe them, they just failed. For example, a positive charge is an electric monopole. There is a single charge. The electric field lines start from it. A negative charge, an electron is an electric monopole. Electric field lines enter it. Here, this is a dipole, meaning two poles. It has a north pole and a south pole. Electric dipole, we had discussed the electric dipole. It has two poles, one positive pole and one negative pole. But just a single positive charge, it's a monopole. There's a single pole. Now, of course, okay, this is how we will show them. Creating the uniform magnetic field. Now, it's the easiest magnetic fields that you can study, or the easiest things you can study are just constants. Uniform electric field is easy to study, easy to manipulate. If we could create uniform magnetic field, that would also be easy to discuss. But it's kind of not so easy to create a uniform magnetic field. It's just, you have this shape. The closest we have is, in fact, this one. If you have two magnets, just approach the north pole of one to the south pole of the other one. Keep them separated. So if you have a north pole here and the south pole here, the magnetic field lines, at least close to the center, will be more or less uniform. Of course, as you go towards the edges, they will get some deformations. These are what's called the fringing effects. But as long as you stick to the region close to this, close to the center, you get more or less a homogeneous magnetic field. Now, we said that if you have a dipole, a current carrying wire, where is it? If you have a current carrying wire close to a magnet, it exerts some force on the magnet. Well, the easier thing to measure would be the other way around. So if the current exerts a force on the magnet, Newton's third law just tells us that the magnet should be exerting a force on the current itself also. So let's see what this force will be. Well, let's just imagine we have what's called a U-shaped magnet. This is the North Pole, this is the South Pole. Well, the magnetic field lines in between will be more or less homogeneous, let's say, more or less uniform. And now let's imagine you put some wire. You pass a wire, send some current through the wire, and then you can just measure the force exerted on the wire. And the force turns out to have this form. Well, first of all, the direction of the force when you send the current through it is not in the direction of the magnetic field lines. You see, that is one difference from the electric field lines case. If you have an electric field in a region, the force that a charge you put in that region will be either in the direction of the electric field or in the opposite direction. If the charge is positive, the force that it will feel will be in the direction of the electric field that is tangent to the electric field line. If it is negative, then it will be pointed in the opposite direction, still tangent to the electric field line. But the force due to the magnetic field turns out to be perpendicular to the magnetic field line. So it's both perpendicular to the magnetic field line and also perpendicular to the current. So it's not in the direction. So if we want to write the force as a vector quantity, it should be somehow related to the B, the magnetic field, but it should also be perpendicular to it. Does that sound familiar? We are looking for some operation which will give me a vector who is perpendicular to another vector. Cross product. And in fact, the force is written in this form. I times L cross B. Now let's see what these things are. Now let me just show let's say this is my wire. Let's assume in the region of the wire there is a magnetic field pointing towards you. I will show it in this sense, in this way. It's like the tip of an arrow. We have a uniform magnetic field, a uniform applied magnetic field. Let's assume also that this wire is, let's say, it goes out. You have a circuit which creates this current. You have a battery. The magnetic field is everywhere, almost everywhere. Now, the force, we said that it is equal to I. So basically, the larger the current you have, the larger the force will be. The length vector cross B. This is the length vector. To specify a vector, you basically need to specify two things. You need to know its direction, you need to know its magnitude. The magnitude of this vector is just this length. This is the magnitude. And the direction of this vector is the direction of the current. So the L vector in this system is this one. So the current we had already discussed last week, in the previous weeks. That is the length vector. And now we have we had already, let's say, not defined yet, but we already discussed the existence of the magnetic field, and it's pointing in your direction. Let's just assume we know the magnetic field somehow. And then this will give us the force. Then, of course, there is the cross product. What does the cross product mean? So let's review the cross product. Whenever we will be discussing about magnetic fields, we will always be discussing about this cross product, one way or the other way. So this, let's say we have two vectors. We take their cross product. The cross product gives me a third vector. Now, you were asking some comments. Well, I read the first question of 300 papers. I don't know which ones are yours, but some common mistakes was, for example, in one of the questions there, you were required to find the potential. The part C was related with the potential, and quite a number of students put a vector sign on the potential. Well, a potential is a number, just a number. It doesn't have a direction. It's not a vector. So if you get a vector as a result of your calculation of the potential, then that means you are doing something wrong. Okay, so let's go back to here. Let's say we know A and B. We would like to calculate C as the cross product of A and B. Well, of course, this C being a vector, we have to be able to find two quantities. One, its direction. Second, its magnitude. So if we know these two things, then we know what this vector C is. Let's say this is my vector A. This is my vector B. And there is this angle in between them. Then the magnitude of A cross B magnitude of C is just twice that area. This area over here. I have a triangle over here. The magnitude of C is just twice that area. Well, what does that mean? The area is this length, A, multiplied by this height. Well, that height is just B times sine theta. Times 1 over 2. So the magnitude of A cross B is A times B times sine theta. Well, if you compare with the scalar product has A times B times cosine theta. The cross product or the vector product has this sine theta. And so this is the magnitude. What about the direction? Whenever there is a cross product, your right hand is your best friend. Take your right hand. Everyone, I want to see your right hands. Right hands in air, not on paper. Okay, point your fingers, 4 fingers, in the direction of the first vector. Well, that's pointing in that direction, such that your palm is kind of pointing towards the other vector. And when you curl your fingers towards the other vectors, the second vector, your thumb points in the direction of the cross product. So in this case, A cross B, if A is on the screen, B is on the screen, A cross B is pointing towards you. This is A cross B. Well, what is the direction of B cross A? Calculate using your right hand. First, in the direction of the first vector, such that your palm should be pointing towards the other vector, and curl your finger towards the other vector. The direction of your thumb is the direction of A cross B, B cross A. Now, A cross B is always perpendicular to A, and it is always perpendicular to B. So if you take the cross product of two vectors, the final vector that you obtain is perpendicular to both of them. So already if you have, let's say, two vectors, and the vector perpendicular to these two, let's say these two, should be either pointing in that direction or pointing in this direction. Should be along this line. And to determine which one, this one or that one, you use your right hand. First, four fingers in the direction of the first vector, your palm pointing towards the other vector, then your thumb points in the direction of the cross product. Let's do some examples. I hat cross K hat. This is X, this is Y, this is Z. This vector here is our I hat. This is our J hat. This is the K hat. I hat cross K hat. I want to see your right hands trying to figure out the answer. You see, let's say I is towards you. I is towards you. K is pointing. No, yes, K is pointing towards you, so just rotate your hand such that your palm points in that direction. It's in that direction. That is over here. Minus J. J hat cross K hat. I want to see your hands, all of yours. J hat, just first your fingers in the J hat direction. If your palm is not pointing in the direction of K, just rotate it. You can, if you want, bend your hand such that your palm points in the direction of the second vector. Then your thumb is in the direction of the result. So JK is I. Well, there's an easy way to remember this. As long as, just imagine these on a circle, as long as the order is IJK, the sign is always plus. So IJK plus. Now this is I. I cross J cross I. Well, these are in the wrong order, so minus. if you go clockwise sense, the order of these symbols should be I, J, K. Now we can ask, why the right hand? Why not use the left hand rule? Yeah, we could have defined it that way. Why do we have the right hand rule? The answer has nothing to do with physics. The majority of physicists were right-handed. That's why we have the right-hand rule, not the left-hand rule. We could have devised all the physics laws, all the magnetic laws, etc., with our left hand, and it would have worked perfectly well. But the convention is we use the right-hand rule. So using these, okay, this is one mean of obtaining the cross product. But you have probably realized in the midterm, quite often we will ask you to show some vectors using unit vectors. Well, the same we will ask with the cross products. So let's say if you have a vector A, which is, let's say, I hat minus 3j hat, and the vector B, which is 3j hat minus 4k hat, then we can ask you, what is A cross B? Well, I cannot even imagine the direction of this A and the direction of B. So the use of this geometrical meaning doesn't really help us much. But we can use the cross products of unit vectors. So let's try to calculate them. A cross B is equal to I hat minus 3j hat cross 3j hat minus 4k hat. Well, it's just like ordinary multiplication. We will just distribute over the summations, keeping the order intact. So it's I hat cross 3j hat. I just multiplied this one and this one in that order. This is the first one, this is the second one. So I'm not changing their order. Then I have this one multiplied with this one, again, exactly in that order, plus I hat cross minus 4k hat, plus I multiply this one with this one, minus 3j hat cross 3j hat, and finally this one with this one, plus minus 3j hat cross minus 4k hat. And all of these ones are hats. So let's start. The first one, 3. What is I hat cross j hat? K hat. 3k hat minus 4 I hat cross k hat plus or minus. Well, let's see. I hat cross k hat. We had already calculated to be minus. Just try to remember this order, ijk. Ik is the wrong order, so I get the minus sign. And then minus 9, what is j hat cross j hat? Why? Well, you see, the magnitude of this vector is proportional to the sine of the angle between the two. What is the angle between the two? 0. So sine of 0 is 0. So that cross product is 0. And then we have plus 12 j hat cross k hat I hat. So that's A cross B is so 12 I hat plus 4 j hat plus 3 k hat. How do you use the determinant? Oh, you mean, sure. If you are more used to the determinant, fine. But I'm not assuming that you already know the determinant. So if you don't know the determinant, just this way works all the time. Now, any questions? So let's go back. What is the direction of this force? I want to see your right hands. The magnetic field is pointing towards you. So point your fingers in the direction of the force. Okay, I want to see the right hands if you haven't figured out the direction of the force. If you have figured out the direction of the force, make sure that your thumb is pointing in that direction. You see, this is also another way of calculating the cross product. But I always fail to remember which one was which. So I just ignore it. I suggest you to do the same. There are rumors that some of the students fell down from their chairs trying to align these. Okay, back to our question. What is the direction of the force? L is in that direction. Now I should rotate my palm towards the direction of B. B is in that direction. My thumb is pointing upward. That is the direction of the force. Now let's do another example. Let's say we have a region of space where there is a uniform magnetic field. By the way, let's go back to this example, this question. This wire is also inside the magnetic field. What is the direction of the force acting on this wire? Well, let's say L is now in this direction. L is, this vector is along the wire in the direction of the current. So it's in that direction, L. B is pointing towards you. L, B, so the force is in that direction. The force acting on this segment. What about the force acting on this segment? Well, the L is pointing downward. So I have to rotate my palm in the direction of B. It's in this direction. There is a force acting on this segment towards the left. There is a force acting on this segment pointing towards the right. And the force acting on this segment is upward. Okay. Now let's imagine a more complicated wire. We have two straight segments. And then we have an arc of radius, let's say, R. And the current is I. What is the total force acting on the wire? Well, you see, the difference from the previous example is that in the previous case, You see here, wire is always pointing in that direction. It's not changing so that we can use the L. But now, in this example, the wire is bending. We cannot just use the previous expression. But the trick is always the same. Just take a very small segment that is straight. I will just divide this arc to very small segments. Each one of those very small segments is now straight. Since they are straight, I can use the previous expression. Let me take this segment over here. This is my dl. I have this very small segment. The current is running in that direction in that segment. The length is the length of it has a very small length, and then I define this dl vector to be pointing in that direction. The force acting on that very small segment will be I dl cross B. So this is the force acting on that segment. What is the direction of that force? Towards inside or towards outside? Well, let's see, 4 fingers in the direction of dl. Rotate your hand without changing the orientation of 4 fingers such that your palm points in the direction of B and your thumb would be in the direction of the force. So this is the direction of df. It goes towards the center, since it's a circular arc. It's perpendicular to this segment, so it should go towards the center. Well, it will have the forces corresponding to each one of these segments will be pointing in different directions. And eventually we will need to just sum all of them up to obtain the total force. So let me just choose my axis first. This is the x-axis, this is the y-axis. And let me write the components of this force. Let's say, let me choose an angle. Let me call this angle my theta. So what is the magnitude of the F? Let's say the magnetic field is B. What is the magnitude of the F? I times B times dl. What is the angle between B and dl? Sine of which angle? You see, dl is pointing in that direction. B is pointing in that direction. What's the angle? This angle is just 90 degrees. So sine of pi over 2, which is nothing but 1. So the magnitude of the force is I times B times dl. What is the x component? What can you say about the x component? We already have determined the magnitude, and we define theta to be that angle. So the x component is, well, if it would be more easier for you, let me just draw a parallel line over here. And this angle over here is also theta. You see, this is my x-axis. Or this is also my x-axis. This is my vector. My vector makes an angle theta. This angle over here is theta with the x-axis. So if I would like to calculate this component, I multiply the magnitude with with the cosine. IB times dl times cosine theta. In which direction is it? It's in the minus I direction. Then I have plus IB times dl. I'm looking for the vertical component, the y component. So I need this length. How can I obtain that length if I know the magnitude? The magnitude times sine or cosine? Sine of theta. So you see, there I have such a triangle. This is my df. I imagine the horizontal line and the vertical line. This is my theta. This length is df times cosine theta. And this length is df times sine theta. And the direction of this one is minus j. No, sorry, this is the second line is dfy. This is df. This is the force acting on the wire due to this very small segment. Well, the total force will be just the sum of all of them. This is equal to I times B is a constant minus I is a constant dl cosine theta plus I times B times minus j dl times sine theta. I'm just summing all the components. Well, L and this, if I change my segment, theta will be changing. Now I need to relate them somehow. Now let me just draw that arc over here. So here I took this segment that has a length dl. This angle is theta. Well, this angle over here, let me call that d theta, is how much theta changes as I go from one segment to the other segment. Then what about dl over r? This is r. You see, the angles are always defined as, at least in terms of radians. If you have an arc, if you know the arc length that an angle sees, if you divide that arc length with the radius, you get the angle. In this case, it is d theta. Or dl is equal to r times d theta. And let me also remind you that since dl is positive, d theta should be positive, which means that when I'm summing over all these segments, I should be increasing theta. So the force, now we know the force, IB times minus I. dl is r times d theta, cosine theta. And theta, what is the first value of theta? 0. I start from this segment. I increment theta. I go up to there. And theta is, when I reach over there, what is theta? Pi. So theta goes from 0 to pi. Minus j hat r d theta sine theta from 0 to pi. This is our force. Well, the second line is 0. The first line should just give us some minus 2. No, sorry. The first line, this is 0. The second line gives just 2. Minus b I r times 2 in the j hat direction. Any last questions? Okay, see you on Thursday.